To consider the effects of C1, C2 and CE. These are the three capacitors whose effects have to be considered in a BJT, and in an FET C1, C2, the two coupling capacitors, and the bypass capacitor is C what? What is the subscript? No. Sigma. C sigma. Okay. We start with the BJT. The usual circuit is VS RS. We consider a common emitter circuit. As usual, this is C1. There are two resistances here, R1 and R2. This goes to plus VCC. We have a resistance R sub C. This is the transistor, and there is an R sub E shunted by a CE. Then we have the coupling capacitor C2 and the load RL. This is V0. This is the common emitter BJT circuit which we used to analyze at low frequencies. We have done its analysis at midband where all capacitors were ignored, that is C1, C2 and C were shorts and C pi, C mu and C0 are open. This is the midband situation. In the high frequency situation we considered C1, C2, C as short, only the effects of C pi, C mu and C0. Now we go to the low frequency situation where it is only these three capacitors whose effect has to be considered. Now I must point out that in integrated circuits one is not allowed to use capacitors, and we have seen different kinds of circuits, at least for biasing, with the help of current mirrors or current sources. There coupling capacitors are not permitted, and therefore what you have to do is to adjust the DC levels such that the DC level of the previous stage does not affect the biasing of the next stage, and therefore you require current mirrors, you require what are known as DC level shifters and things like that. We shall come to those when we consider op-amp circuitry in this class, but at the present time, at least in discrete circuits, we have to consider the effects of C1, C2 and CE. Now a few qualitative remarks before we go to the actual analysis. You notice that there are three capacitors, and if we draw the equivalent circuit, you will see that these capacitors are independent of each other. C1, C2 and CE are independent of each other. One does not affect the other. They are not connected in series or in parallel that we can combine. Okay, they are independent capacitors, and therefore what we expect is that there shall be three poles corresponding to three capacitors, and qualitatively you can see that C1 will have a high pass effect. Obviously the DC response, DC cannot pass through C1, so if the signal is at zero frequency, no signal shall come to the transistor, and at high frequencies C1 acts as a short, so it has a high pass effect. High pass effect means that in the denominator we expect a term like 1 minus j. Is it omega by omega 1 or omega 1 by omega? No, it is omega 1 by omega. At DC, when omega is 0, it should be 0. Isn't that right? High pass filter. I did this at the beginning of this discussion. CR, series C and shunter, this is the kind of factor that you get, 1 minus j omega 1 by omega. Alright. Similarly, due to C2, which also blocks DC, there shall be another high pass effect, and therefore we expect another term 1 minus j omega 2 by omega, alright, due to C2. But due to CE, CE comes in shunt, and therefore it shall have a low pass effect. It should have a low pass effect. CE comes in shunt, okay, series resistance, shunt capacitance, this is a low pass effect. But you see that even if CE is equal to infinity, the gain is not 0. there is a gain, okay, and therefore it's not quite pure low pass. Also, if C equal to 0, even then there is a gain, so it's not high pass either. Do you understand this? No. If C is infinity, okay, if C is infinity, there is a gain. The gain is larger, the gain is the mid-band value if C1 and C2 effects are neglected, okay. If C is 0, then the gain drastically reduces because unbypassed emitter resistance, but there is a gain, the gain is not 0. So it is neither low pass nor high pass, it's something in between. And as we shall show, the effect of CE, well, effect of C1 is to introduce a factor 1 minus, why minus? Because omega occurs in the denominator. It's actually 1 plus omega by j, omega 1 by j omega, and this j we have brought it up, multiplied by 1 minus j omega 2 by omega. This is due to C1, due to C2, due to CE we shall have a pole of the low pass type 1 plus j omega by omega 3 and a 0, that is 1 plus j omega by some quantity omega 4. These two come due to CE. These are the poles and zeros. There is a pole and there is a 0. The pole is of the low pass type.
So this here C2 is in series with R2, but isn't it in parallel with R2 also?
C2 is in parallel with
R2 also.
Where is R2?
Sorry, RC.
C2 is in parallel with RC. That's fine. In the equivalent circuit. No, it is not in parallel. RC will come from here to ground. RL is from here to ground. C2 is the bridge. C2 is not in parallel with RL. We will see this in the equivalent circuit. But qualitatively, an ingenious best tool is what? Number 1. Number 2, how does he obtain the approximation? Observation. Common sense? Okay, common sense. Common sense and observation. As I said, there is a difference between seeing and observing. It's not, yes, I'll tell you this story later. But so we want to look at it and see what is it that we expect. Because CE comes in shunt, it goes to ground, it should have a low pass effect, and this is what is expected from this. On the other hand, CE also creates a 0 because it's not pure low pass. The gain is neither 0 at infinity nor at the origin. So it's neither a pure low pass nor a pure high pass. In fact, it's a combination, as we shall see. Number 2, if omega 4 is infinity, which will occur when CE is equal to 0, okay, this will occur when CE equal to 0. If omega 4 is infinity, then obviously this term shall be absent. There still shall exist a gain which we shall not characterize at the moment. We will simply call it a constant, and this is what we expect for AVS j omega. Expected. Now let's see one by one what happens. Obviously, if you want to draw the equivalent circuit, let's draw the equivalent circuit, then perhaps the magnitude of the problem shall be absolutely clear. The equivalent circuit is Vs Rs, we have a C1, then we have the parallel combination of R1 and R2, which will be RB. We ignore Rx because that creates a lot of complication. We ignore Rx. We have an R pi. Now I don't bring it to ground because we are considering the effect of CE, all right. R pi, and the voltage across this is V pi. Then we have a GM V pi in parallel with R0. This point is not grounded. From this point we have the parallel combination of two components, RE and CE. RE and CE, and then from this, which is the collector point, we have first C2, first RC to ground, the biasing resistance, then C2, and then an RL. We cannot combine RC and RL now because there is a bridging capacitor C2, and this is the voltage V0 that we want to find out, and our aim is to find AVS, which is equal to V0 divided by Vs. Obviously, if you have to do an exact analysis of this, how many nodes do you have to consider? 1, V0. Well, actually V0 by Vs we want to find out. So this, we don't write a node equation here. We write a node equation here, 1, then another node equation here, 2, and a third node equation would be here, 3. 3 node equations are required, and therefore you will have to invert. If you do by node analysis, you will have to invert a 3 by 3 matrix, which is pretty tough. So engineering approximation comes into effect. What we shall do is, first we will consider the effect of each capacitor independently of the others. In other words, when we consider the effect of C1, we shall assume C2 to be short and CE to be short. Alright, then we consider, we will justify the procedure later. As I said, engineer often justifies his procedure by the end rather than logic, by the end result. If there is nothing, there is no success like success, and therefore if you succeed, if you get an approximation which is valid in practice, well, your procedure is valid. Okay, it's gross, logically absolutely not correct, but an engineer has no other way. He doesn't want to make life complicated. After all, even if you do this analysis by using a SPICE computer program, for example, or any other existing subroutines, you will have to make adjustments ultimately, and therefore engineering approximations are required. So what we will do is we will consider the effects of C1, C2 and CE one at a time. That is, when we consider the effect of C1, we assume C2 to be infinite and CE to be infinite, so that the act is short. When we consider the effect of C2, we consider C1 to be infinite and CE to be infinite. Okay. Similarly, when we consider the effect of CE, we shall assume these two to be short. Then we will try to combine. Okay, then we will try to combine, and this combination is very illuminating. It's also a very bold step, but it works. So let's see first the effect of C1. In considering the effect of C1, we consider CE as a short, therefore this point will go to ground and this will be a short. Alright, let us see what happens to this equivalent circuit. We have a Vs, effect of C1, where we assume C2, CE both go to infinity, that is, they are shorts. I have an RS, a C1, and from here I have RB and R pi. We had already combined these two into a single resistance, capital R subscript pi. Okay, this is V pi, voltage across RB, and then we have a GMV pi going to ground. And if you look at this now, let's do this simplification right away. If you look at this circuit, C2 acts as a short and R0 goes to ground, and therefore R0, RC and RL come in parallel, which we can combine into a single resistance RL prime, and this is V0. RL prime equal to R0 parallel RC parallel RL. Once again, an engineering approximation, because it is possible to include R0 without much of a complication, we are including it. If it is not convenient, then you will say R0 is very large. You understand? Okay. Life is approximation and electronic circuits is no exception. Alright. Now to calculate the gain, that is AVS, which is equal to V0 by Vs, I can write V0 by V pi multiplied by V pi by Vs in 2 steps, alright. And the first factor V0 by V pi is simply equal to minus Gm RL prime, alright. So we have to calculate V pi over Vs. That's not also a difficult story, because there is a potential division between RSC1 and R pi, okay, R pi. Therefore, we can write AVS as equal to minus Gm RL prime, then the potential division I can write as R pi divided by R pi plus Rs plus 1 over j omega C1, agreed? And the effect of C1 is obvious, that is equal to minus Gm RL prime multiplied by R pi divided by R pi plus Rs. I take R pi plus Rs common, then we have 1 divided by 1 plus omega 1 divided by j omega, where omega 1 is equal to 1 over C1 multiplied by R pi plus Rs. Is that okay? All we have done is we have taken R pi plus Rs, so 1 by j omega C1 R pi plus Rs, and 1 by C1 R pi plus Rs we have put as the constant omega 1, alright. And this j in the denominator can be written as, with a negative sign, we can make this negative and bring j here. Also notice, what is this factor? This is the mid-band voltage gain, AVS 0, alright. So I can write AVS as equal to AVS 0 divided by 1 minus j omega 1 divided by omega, alright. As expected, this is a high pass filter, and if C2 and CE indeed go to infinity, then omega 1 will be the 3 dB low frequency, 3 dB cutoff frequency, okay, low frequency 3 dB cutoff. That is, if I plot AVS versus omega magnitude, then at mid band it will become magnitude AVS 0 and 1 by root 2 this will be reached at omega 1. It is a high pass effect, alright. Any question on this? This was very simple. One thing that I want to point out here is the following, that this omega 1 is the reciprocal of a time constant. Omega 1 is the reciprocal of a time constant. And how do you determine the time constant? If you look at this circuit, the time constant is associated with the capacitor C1, and the resistance that comes to multiply C1 is the sum of Rs and R pi, which means that this is the resistance seen by C1 in a Thevenin equivalent sense. That is, resistance seen from the terminals of C1 with independent sources eliminated, which means that Vs has to be shorted. If Vs is shorted, then Rs comes in series with R pi, alright. So this time constant is determined by C1 and the Thevenin resistance that C1 sees into this circuit, okay. This interpretation shall be useful at a later point of time when we have, let's say, 9 capacitors in this circuit, and node analysis or loop analysis is going to be extremely tough. We will have to use some shortcuts like this, engineering approximations. Okay, let's look at the effect of C2. When you consider the effect of C2, our equivalent circuit, now C1 and CE are shorts, and therefore our equivalent circuit would be Vs, Rs, no C1 is a short, and then we have simply the parallel combination of RB and R pi. So we have called this as capital R pi, this is V pi, then we have Gm V pi, okay, then now you have to be careful, R0, then an RC, now comes C2, and you have an RL. This is V0. Obviously, one can simplify this circuit very simply, that if you apply Thevenin's theorem to the left of this line, then you get a voltage source Gm V pi multiplied by the parallel combination of R0 and RC with a negative sign, and the Thevenin equivalent impedance would be simply the parallel combination of R0 and RC. Okay. So if I do this, let me write this down here, minus plus, the value would be Gm V pi R0 parallel RC, and in series with a resistance which is R0 parallel RC. If I do that, then you see R0 parallel RC comes in series with C2, and then you can find V0 as a potential division, alright, and V pi of obviously is Vs multiplied by R pi divided by R pi plus Rs. Okay. So a Vs can be written down by inspection. Is that clear? Can I repeat? Okay. V0 I have to find out in terms of V pi. I have applied Thevenin's theorem here to the left of this line. So a voltage source and a series resistance R0 parallel RC, which comes in series with C2 and RL. Therefore, I can find V0 in terms of V pi, and V pi in terms of Vs is simply the potential division between Rs and R pi. So the expression for AVS can be written down by inspection, and you will have to do that as our course proceeds. We are not going to derive everything. It would be simply minus Gm R0 parallel RC. Okay, let's find out first the output voltage V0 in terms of V pi. This would be RL divided by RL plus R0 parallel RC, then plus 1 over j omega C2. This is V0 by V pi. Then this should be multiplied by V pi by Vs, which is R pi divided by R pi plus Rs. Agreed? Okay. Now you notice something interesting, that I can write this as minus Gm R0 parallel RC multiplied by RL divided by RL plus R0 parallel RC. Okay, I have reproduced this term, I have taken RL and I have taken from the denominator this term, and then let us introduce this also, R pi divided by R pi plus Rs. What remains is 1 divided by, what remains? 1 plus omega 2 divided by j omega, where omega 2 is 1 over, yes, C2 multiplied by RL plus R0 parallel RC. Agreed? And if you look at this expression carefully, what is this expression?
R0 parallel RC parallel.
That's correct. And therefore, I can write the gain, low frequency gain, AVS, in this form. I can write minus Gm R0, well, okay, RL prime, wonderful. Is this point clear to everybody?
Yes.
Okay. Gm RL prime multiplied by R pi divided by R pi plus Rs, and obviously this is equal to AVS 0 divided by 1 minus J, that J in the denominator we bring it up, so it becomes minus omega 2 divided by omega, where omega 2 is equal to 1 over C2 RL plus R0 parallel RC. Okay, and I have got again, I have validated the fact that C2 has a high pass effect. That is, if C1 and CE are shorts, then C2 causes the DC response to be 0, and then it rises like this at high frequencies. Again the gain is AVS 0 and the cutoff occurs at omega 2, alright, omega 2. If we combine, before we combine, you note again that C2, omega 2 is the inverse of a time constant, and the time constant is the product of C2, the capacitance, and what resistance does come in parallel. If you look at this circuit, what resistance comes in parallel with C2, multiplies C2? It is RL plus the equivalent of this. Now, isn't this the Thevenin resistance that C2 sees? Because this is a current generator, and Thevenin resistance Vs equal to 0, so V pi equal to 0, so this current is 0, and therefore what you see is C2 in parallel with RL plus R0 plus RC. Okay.
So in the previous case also, on one side of the capacitor we had one resistance and two resistances on the other side.
Okay, we combine them.
And we combine them all together by saying that
They come in series.
they come in series.
Here also they come in series. What C2 sees is, this is open, this is open, so what C2 sees is RL plus R0 parallel RC. Same story. Okay, so this is another interesting and important observation which we shall utilize at a later time. That is, this frequency, this cutoff frequency is contributed by C2 along with what resistance what Thevenin resistance it sees across it. And now if I combine C1 and C2 together, I can make the engineering approximation AVS equal to AVS 0 divided by 1 minus J, one frequency due to C1 and the other frequency due to C2. Question is whether we should write this, we should put this with an approximation sign or not. Should I put an approximation sign here, or is it exact? Effect of C1 and C2 together. In both of them I found that if I ignore C2 and CE, then I get this expression. If I ignore C1 and CE, I get this expression. Now I am making a combination. I claim that this is exact. No such thing is needed. If you had considered C1 and C2 together, it would have been the same story. If you differ from me, let me know your logic. Okay, I claim that this is an exact expression. However, CE creates problems.
So, but what is the logic behind it being exact?
You find it out. Why should I answer all questions? Effect of CE. Actually carry it out and see that this is exact. This happens, the logic, okay. Not the logic, the clue. The clue is that the input and the output circuits are isolated from each other. So they don't interact with each other. C1 does not affect C2, C2 does not affect C1. And therefore you can calculate the input cutoff frequency, output cutoff frequency independently, and this is the story. Alright, there is also an engineer's eye which has to detect that this is an exact expression. Okay. Now when we consider the effect of CE, we have a problem. Look at the effect of CE, we consider C1 and C2 to go to infinity. Okay, let's look at the equivalent circuit. Then the problem then the problem that is in our hand shall be clearly understood. We have an RS and we have
C1, C2 goes to 0 or
infinity. They act as short circuits. We are not considering their effects, okay? Alright. Now we cannot combine RB and R pi, unfortunately, because CE is not a short circuit, and therefore we have to consider them independently. RB and then an R pi, this voltage is V pi. What comes here is a parallel combination of RE and CE. Wait a second, we have not come to that yet. Then we have the GM V pi, and since this is the collector, there shall be a resistance R0 across GM V pi. Alright? And then we have C2 is short, therefore we have RC in parallel with RL. You see the problem now.
The input and the output are not isolated this time.
They are not isolated this time. They are coupled through RE and CE, and therefore the circuit is a bit more complicated than the two circuits that we had considered. However, some simplifications are possible. Now an engineer applies his common sense. He says if R0 is included, life becomes unnecessarily tough, because this current generator will be shunted by R0, and R0 cannot be combined with RC and RL because there is something else here. So we assume, first thing we assume is R0 goes to infinity, and we say RC parallel RL. If you want to use another notation, you are most welcome to do it, but I will use an RL prime which is correct because we are assuming R0 to go to infinity. So this is RL prime. Now things become a little simplified, because then V0, as you can see, is still equal to minus GM V pi RL prime. V0 is minus GM RL prime V pi. So what you have to find out is V pi. V pi divided by Vs. However, no simple potential division occurs anymore. No, because there are two resistances here. However, this can be taken care of because the great man Thevenin has supplied us with a tool which we can reduce this to a voltage source and an equivalent series resistance. Let us see what this equivalent circuit now becomes with these simplifications. Is this point clear? We apply Thevenin to the left. Then we get Vs prime, which is equal to Vs Rb divided by Rb plus Rs. Okay, a voltage source Vs prime in series with a resistance which is Rs prime, which is the parallel combination of Rs and Rb. Then we have an R pi, the voltage across which is V pi, and instead of the writing two elements Re and Ce, let us write their equivalent impedance. I call this Ze. What is Ze? Ze is, if you recall, Re divided by 1 plus j omega Re Ce. Alright. So we are writing the impedance because we will require this. We will require this, and then we have a GM V pi and RL prime. RL prime, this is V0. Okay, the current through this combination Ze is obviously GM V pi plus V pi by R pi. So it would be V pi times GM plus 1 by R pi, which is beta plus 1 divided by R pi multiplied by GM. No more GM. That's it. V pi beta plus 1 divided by R pi. Okay. So what I do now is to write a KVL. What I have to find out is I have already found out V0 by V pi. This is minus GMRL prime. What I have to find out now is V pi divided by Vs. So if I write a KVL around this slope, then I get Vs RB divided by RB plus Rs. This is Vs prime. This would be equal to Rs prime, which is Rs parallel Rb, multiplied by, what is the current through this? What is Ib? I don't want another notation, another symbol, V pi by R pi. Okay? This is the drop in this resistance, then plus the drop in R pi is V pi. I don't have to write V pi by R pi multiplied by R pi, it is V pi, plus the drop in ZE, which is V pi beta plus 1 divided by R pi multiplied by ZE, which is RE divided by 1 plus j omega RE CE. This is the equation that will give us V pi in terms of Vs, alright, and we already have found out V0 equal to minus GM RL prime V pi, and therefore one can find out, one can simplify and find out AVS, which is Vs divided by, V0 divided by Vs. Okay, I will skip this algebra and I will write the final result like this. You do this algebra yourself and you can write the final result as follows. If I have made a mistake, you will have to point out to me. Minus beta RL prime RB divided by RB plus RS divided by RS prime plus R pi plus beta plus 1 RE. This multiplied by 1 plus j omega by omega 4 divided by 1 plus j omega by omega 3, where I will give you the values. The values are omega 4 is equal to 1 over CERE and omega 3 is equal to omega 4 multiplied by 1 plus beta RE divided by RS prime plus R pi. This is it. Now this expression is not as simple as the earlier ones. It has a pole and a low pass kind of a pole, because omega occurs in the numerator, j omega by omega 3. It is not omega 3 by j omega. So it is a low pass effect, but it has a 0 also at s equal to, where is the 0? At s equal to minus omega 4. Okay, so it has a 0 also, and therefore when omega tends to 0, the value of the gain, these two terms shall disappear. The value of the gain would be simply this term. We call this as AVS 0 1. All right, that is when omega tends to 0, this term drops out, so we call this AVS 0 1. On the other hand, when omega tends to infinity, the gain will again be a constant, but this value shall be AVS 0 2. This would be, that's right, AVS 0 1 multiplied by omega 3 divided by omega 4. Do these stand to reason? If you simplify this, you shall see that AVS 01 is the gain of the common emitter amplifier with unbypassed resistor. Omega tends to 0 means what? Capacitor CE is open. All right, and you can show that this is approximately minus RL prime by RE. You can see this immediately right from here. Okay, so AVS 01 is the gain of the common emitter amplifier with mid-band gain of the common emitter amplifier with unbypassed emitter resistance. Is the point clear? Omega tends to 0 means CE is open, so RE is not bypassed. This is equal to mid-band gain with unbypassed RE. On the other hand, when omega tends to infinity, CE is short. CE is short, and therefore AVS 02 should be equal to what? Mid-band gain with emitter grounded. Emitter grounded. And this was the real mid-band gain that we had calculated. We had assumed that C1, C2 and CE are short circuits, and therefore can you guess what this would be? Minus GM RL prime multiplied by R pi divided by R pi plus RS. All this we talked about from the expression and from common sense. You can actually show that this is true. All that is required is to manipulate this expression and the ratio omega 3 by omega 4. Which one is greater? Of these two, which one is greater? 02. Why? Because omega 3 is much greater than omega 4. Much greater. Why? Because beta plus 1 RE, R pi and RS prime, they will be of the same order of magnitude. And therefore this factor shall be approximately half. So it is beta by 2, which is typically 50. So it is 51 times omega 4, which means that omega 3 is much greater than omega 4, is much greater than omega 4. But it shows that if we plot this expression, the magnitude versus omega, what kind of a plot shall we get? What kind of a plot shall we get? If we plot AVS magnitude versus omega, then at DC it is the gain with unbypassed RE, AVS 01, and at infinite frequency it is greater than AVS 01, it is AVS 02. So you will have something like this. It is a kind of high pass. It is a kind of high pass. Now where will these frequencies omega 3 and omega 4 be? Omega 4 obviously would be somewhere here, okay. Omega 4 would be somewhere here where the curve just starts to rise. This would be approximately omega 4, and omega 3 would be somewhere here approximately, okay. So omega 3, this is now a kind of a low pass, a high pass effect. This is a kind of a high pass effect, and since omega 3 is much greater than omega 4, they are non-interacting, which means that if C1 and C2 are short circuits, CE has the effect of producing a high frequency 3 dB cutoff at omega 3, okay. So our situation is that we have a omega 1 due to C1, we have omega 2 due to C2, we have a 0 at omega 4 due to CE, we have a pole at omega 3 due to CE. So who will determine the low frequency cutoff? Obviously of these 4 frequencies, who will determine? How do you know?
So only we will exclude omega 4.
We shall have to exclude omega 4 because omega 3 is much greater than omega 4. Okay, so omega 4 does not determine. So who will determine that?
The highest.
The highest of these 3 will have the major effect, isn't it? Suppose omega 1 occurs here, omega 2 occurs here. These are of no concern. What we are concerned with is the mid-band gain. Where does it come 3 dB? Below. Okay, let's take an example. Now, would you then agree that our initial guess was AVS would be equal to some constant multiplied by 1 plus j omega by omega 4. This was the initial guess. 1 minus j omega 1 by omega, 1 minus j omega 2 by omega, then 1 plus j omega by omega 3. And remember, we did not put this constant equal to AVS 0. Why? Because it was not AVS 0. It was either AVS 01 or 02, depending on whether you consider omega tends to 0 or omega tends to infinity. Okay? So this constant is not the mid-band gain. All right? Now if we combine all of them, that is C1, C2 and CE, then we will get an expression like this, but this expression will now be actually an approximate expression. Why approximate? Because the input and output circuits are no longer decoupled from each other. We cannot decouple, and therefore this is an approximate expression. And as I said, omega 4 can be taken out of consideration. The high frequency 3 dB point shall be low frequency 3 dB point will be determined by the highest of these three, omega 1, omega 2 and omega 3. Okay? Let us take an example, the same example that we have been considering so far.
So why can't you put this constant equal to AVS 01?
Is this constant equal to AVS 01? Okay. When omega tends to 0, what does this correspond to? 0. This also, I am sorry, infinity, infinity. So this is not AVS 01. Okay? There is a problem. Now we consider the same circuit, that is 2.2K, 1K. Let this capacitor be 100 microfarad. This also shows some typical values that you have to use in practice. Then 2.2 microfarad. You see, this is about 50 times. This is the kind of things that you will have to use. I will tell you why. 4.7K, and you have two resistors, 220K, 220K, then you have a 10 microfarad condenser here, a 600 ohm resistance, we had considered this, and a Vs. Okay, this is the circuit with the numerical values. The GM is given as 39 millimho as usual. Rx is given as 100 ohms, which we have ignored, compared to 2.6K, which is R pi. 2.6K, 2600 ohms, we can ignore 100 ohms. And R0, poor quantity, sometimes is ignored, sometimes is not ignored, depending on our convenience. But we have to apologize to R0 because it makes our life difficult, so we will keep it out of the door when it is convenient. We'll bring it inside when it is not inconvenient.
600 kilo.
Oh, 600 ohms. If it is 600 kilo ohms, nothing will come to the circuit. Sorry, 600 ohms. Okay. Now, if I can consider these effects separately and calculate the various frequencies, I get omega 1, which is 1 over C1. You must remember mentally what C1 says. What C1 says? Rs plus R pi. No. No or yes? Rs plus Rb?
It's okay, capital R pi.
It's okay. All right. For once I am right. Mostly I am right. 31.8 radians per second. That's what it comes to if you put the values. This is equivalent to 5 hertz. Equivalent to. We have to divide by 2 pi. That becomes 5 hertz. Okay. Then that is F1 is equal to 5 hertz. If you calculate omega 2 is 1 by C2 multiplied by its Thevenin resistance, which is RC parallel R0. Okay. This calculates out to 66 radians per second, which is equivalent to 10.5 hertz. Omega 4, that's 0, which is 1 over CE RE. This calculates out to 10 radians per second, which is equivalent to 1.59 hertz. And therefore this is really at low frequencies. Even omega 2 is much, omega 2 10.5 is much larger than this, so we can ignore this. And omega 3, unfortunately, even with 100 microfarad condenser, what is it? Omega 4, that is this multiplied by 1 plus beta RE divided by RS prime plus R pi. This comes as 326 RPS. You see, 31.8, 66, 10 and 326, which is equivalent to 52 hertz. And there is no doubt that FL, that is the low frequency 3 dB cutoff, is dominated by omega 3 and shall be equal to 52 hertz. Okay, this shows that the calculations can be done independently, but you can get a fairly good estimate. Now suppose omega 1 and omega 2 and omega 3 were comparable. If they are comparable, let's say 31.8, maybe this is 40 and this is 50, then you are in a problem. Okay, you have to combine all the three and find out the actual 3 dB cutoff frequency. That is by taking the magnitude and putting the magnitude equal to mid-band value divided by √2. Solve that for omega. What kind of an equation would you have got? What order of equation? Cubic equation in, no, not in omega, that's why I asked you. Omega squared, because magnitude magnitude would contain 1 plus omega, 1 squared by omega squared. Now a cubic equation, can it be analytically solved?
It can be, sir.
It can be solved. It can be solved, but the solution procedure is quite complicated and quite disgusting. So what you do is do numerical approximation. Okay, nevertheless it has to be done. Suppose only omega 1 and omega 2 are comparable, and omega 3 is much lower than omega 1 and omega 2, then obviously you have to solve a quadratic equation. But if one of them dominates, nothing like it. And this is where I am going to now. One was expecting in this circuit that perhaps C2 shall dominate, but alas, contrary to our expectation, it is C3 which dominates, because omega 3 is the cutoff due to C3. Even at 100 microfarad, we could not make it a non-dominant factor. Now this is usually the case that you can afford to use low valued capacitors here, but if you want RE to be bypassed, then this capacitor has to be substantially larger compared to C1 and C2. And 500 microfarad, fortunately electrolytic capacitors can be used because it's a bypass. 500 microfarad is a typical value that is used. We will continue this tomorrow.